Astronomers continue to struggle with uncertainty in their quest to understand the first stars and galaxies that lit up the universe. But with each discovery, we come closer to understanding. This wonderful truth has been discovered through the unprecedented research of the James Webb Space Telescope, JWST, which is now marking its first year of observation at a cost of $10 billion. JWST was designed to show the low infrared brightness of the first bright objects in the universe, and it has exceeded expectations. The Webb Observatory goes back to the first 100 million years after the Big Bang and provides better data on newborn galaxies compared to other previous installations. The variety of galactic baby images has exceeded even the best predictions, with many candidate classes emerging and surprising researchers such as Charlotte Mason, an astrophysicist at the University of Copenhagen. The sudden maturation of these early galaxies has sparked intense scrutiny and speculation among theorists and observers. Could these large and bright early galaxies be an illusion due to errors in early telescope observations? Or, if it is true, can it be included in the models of the universe? In fact, do they point to a universe that is stranger and more complex than previously thought, perhaps challenging the foundations of the Big Bang theory itself? Join us as we learn how the James Webb Space Telescope changed our understanding of the universe. But first, we return to the birth of the world after the Great City. As the universe cooled, electrons, protons, and neutrons combined into mostly neutral hydrogen atoms, ushering in what is known as the cosmic dark ages. Then something great happened. Most of the mass of the universe, including dark matter, begins to gain influence, eventually leading to the formation of the first stars. These stellar beacons illuminated the cosmos during the epoch of reionization, sparking a cascade of events that shaped the evolution of galaxies within a vast cosmic web. Meanwhile, Edwin Hubble's groundbreaking discoveries in the 1920s revealed that the universe is expanding. Subsequent observations, including those from the Hubble Space Telescope, unveiled an even more astonishing truth. The universe's expansion is accelerating, driven by enigmatic dark energy symbolized by the Greek letter lambda. By integrating the properties of cold dark matter, regular matter, and radiation into Einstein's general theory of relativity, scientists have constructed the lambda cold dark matter model, which remarkably aligns with a myriad of observational data. One way to validate this framework is by scrutinizing distant galaxies, akin to peering back in time to the initial few 100 million years after the colossal explosion that set everything in motion. During this period, the world was much simpler and easier for astronomers to compare with conventional predictions. Attempts to observe the first formations in the universe with the Hubble Space Telescope began in 1995. In 10 days, Hubble recorded 342 observations of what appeared to be an empty space, Ursa Major. To the astonishment of astronomers, this dark spectrum revealed thousands of galaxies at different distances and stages of development, receding further than expected. In 2016, astronomers with Hubble made a landmark discovery. The most distant galaxy known at the time, GNZ 11. This faint burst, which dates back to 400 million years after the Big Bang, challenged the understanding of the beginning of the formation of galaxies. However, this model did not significantly disrupt the lambda model, in part because of its small size, which is only 1% of the mass of the Milky Way. However, astronomers needed a more powerful tool to determine whether GNZ 11 was an anomaly or part of a wider group of lost early galaxies. Enter the James Webb Space Telescope, known as the largest and most powerful observatory ever launched from Earth. Located 1.5 million kilometers from Earth's disturbances and cooled to near zero, JWST has a large split mirror and sensitive equipment designed to reveal information never before seen before sunrise. JWST's initial discoveries have already surpassed expectations, offering glimpses of galaxies astonishingly close to the dawn of time and probing exoplanet atmospheres with unprecedented precision. As Webb's vision extends back to the universe's earliest epochs, it promises to yield unparalleled insights into newborn galaxies, potentially reshaping our understanding of cosmic evolution. The implications of JWST's early revelations are profound, potentially rewriting the opening chapters of cosmic history and shedding light on fundamental questions about our existence in the universe. A.S. Mark McCaffrian, a senior advisor for space and exploration at the European Space Agency, aptly noted, These machines are designed not to affirm the status quo but to challenge it, paving the way for paradigm-shifting discoveries. A key method utilized by researchers to assess the distances of celestial objects is a variant of the Doppler effect, analogous to determining the location of an ambulance based on the pitch of its siren. Astronomers measure the redshift of galaxies, where the magnitude of redshift indicates the object's distance from us. JWST's data has already led to intriguing findings, such as the discovery of galaxies with redshift values ranging from 11 to 20, hinting at the possibility of an incomplete understanding of early galaxy formation within the Lambda model. In summary, JWST's unprecedented capabilities have begun to unravel the mysteries of the early universe, challenging existing models and paving the way for a deeper understanding of cosmic evolution. Researchers delved into computer simulations of universes governed by the Lambda model and made a startling revelation. The early bright galaxies observed by JWST were significantly more massive than those simulated to form concurrently. This dissonance sparked debates within the scientific community and drew attention from various media outlets, with some claiming that JWST was challenging the foundations of cosmology. However, not all experts were surprised by this news. One of the challenges lies in the ambiguity of the predictions of the Lambda model. Although topics like dark matter and dark energy are simple, chemistry shows that complex interactions and behavior can be seen, especially in the tumultuous years after the big hit. These chaotic times need a computer nearby. In the months following the initial papers, the ages of some purported high redshift galaxies were reassessed due to updated telescope calibrations. For instance, Sewers 749 was found within a galaxy cluster whose light dates back 12.4 billion years, suggesting it might be a nearer object masquerading as a high redshift galaxy due to dust obscuration. Regardless of its distance, Sewers 749 represents a peculiar case, potentially defying conventional expectations with its low mass yet significant dust content. To obtain more definitive distance estimates, researchers anticipate leveraging JWST's most potent capability, spectroscopy. Unlike photometry, which measures brightness, spectroscopy analyzes the wavelengths of light, akin to conducting a DNA test to unravel an individual's ancestry. While initial observations relied on photometric measurements, combining spectroscopy with photometry for 4 galaxies revealed redshifts up to 13.2, indicating light emitted 13.2 billion years ago. The unveiling of these spectra sparked excitement among researchers, signaling a potential shift in our understanding of the early universe. Brant Robertson of the University of California, Santa Cruz, suggested that these findings imply rapid evolution in the early universe, with galaxies evolving 10 times faster than today, akin to a hummingbird's accelerated heartbeat compared to larger creatures. However, questions linger regarding whether these rapid changes are compatible with the Lambda model. While JWST's images captivated astronomers and the public alike, researchers worked diligently behind the scenes to discern the true nature of the observed galaxies and refine the parameters of cosmological equations. The most important of these parameters is the mass of the early galaxies, which is important for assessing their growth over time and comparing it with Lambda's predictions. Determining a galaxy's mass from its brightness depends on assumptions based on our understanding of stars and galaxies. However, astrophysicist Megan Donahue of Michigan State University cautions that this connection is just speculation. This depends on assumptions about the initial mass function, which represents the statistical range of masses at which stars form. The initial mass function is important to consider because, while hotter blue stars tend to be more luminous, most of the galaxy's mass is contained in smaller, cooler red stars. However, primordial mass behaves differently in the primordial universe. If so, the earliest galaxies observed by JWST may be brighter than they are, which may challenge our understanding of galaxy formation. Rachel Somerville, an astrophysicist at Flatiron University, suggests that changes in the primordial mass function and other factors could account for the older galaxies found by JWST and the Lambda model. He believes that the early universe cooled faster and formed stars faster. Another interesting fact is the role of black holes in the first universe. Glowing supermassive black holes observed at redshifts of 6 or 7, a billion years after the Big Bang, could explain the brightness of early galaxies even if they aren't exceptionally massive. Confirmation that the Lambda model can accommodate some of JWST's early galaxies came from simulations conducted by Benjamin Keller and his team at the University of Memphis. Their findings, reported on the preprint server arcs4.org, indicate that the simulated galaxies align with JWST observations, alleviating concerns about the compatibility of the observed galaxies with the prevailing cosmological model. Furthermore, JWST's discoveries hint at the existence of population 3 stars, the first generation of stars to ignite. These stars, unpolluted by metals from previous stellar generations, may have contributed to the reionization of the universe. The discovery of the largest and oldest galaxies in the early universe, as seen by the James Webb Space Telescope, initially shook astronomers' understanding of the universe. These galaxies, known as universal breaks, defied expectations and raised questions about the validity of the standard model of the universe.